Hello, friends. After a long time, I am now back with another of my videos about the Garnet Group, which is a silicate. And today I shall be discussing about its structure and how can we make the framework structure of Garnet. So let us begin. Now, Garnet is an important mineral that is an integral part of metamorphic rocks, igneous rocks, and sometimes it occurs as detrital grains in sedimentary rock. So, as already mentioned, garnet is a silicate, and all of us are aware of what a silicate is. So, going into some of the uh, introductory part, garnets are essentially silicates of various divalent and trivalent metals. So when I say divalent and trivalent, I'm sure everyone here knows it. The general formula is R2 plus 3 R3 plus 2 SiO4 whole thrice, or it can be written as X3 Y2 Si3O12. Now, to balance this up, we can understand all these, the 2 plus and 3 plus ions. So the divalent ions over here, which are adhered to or which reside in the X site, they are normally of calcium, magnesium, ferrous, and manganese, while the trivalent metals over here or trivalent ions, they are of ferric, aluminum, chromium, and titanium, which reside in the Y side. Okay, these nesosilicates, they belong to the isometric crystal system, and as I've already mentioned, characteristic of metamorphic rocks also found in igneous rocks and as detrital grains in the sedimentary rocks. Garnet, normally it has been found under normal circumstances as six species, but to classify them for an easy understanding, they are divided into two main groups, that is pyralspite and eugrandite. Now, how do we get these names? If you look at how I have written these two names, pyralspite and eugrandite, you can see these are derived from the names of the garnets only. So PYR stands for pyro, AL for almandine, and SPITE for spessartite. While eugrandite, U stands for uaroite, GR for grossular, and ANDITE for andradite. Now, we know the general formula, so very easy to remember over here that in case of the pyralspite main group, the trivalent cation doesn't change. So here you will be having aluminium sitting in the Y side and pyrope. So the X site in pyrope is magnesium, almandine is iron, ferrous, and spessartine is manganese. So you have to remember that pyralspite is the group of the garnets which has trivalent cation as that of aluminium sitting in the Y side. Okay, and pyrope has come from it is a magnesium bearing garnet, almandine is ferrous, and spessartine is manganese. But once we come to eugrandite, here the X site is fixed. It has the divalent ion as calcium. Okay, while in the Y site, Uarovite consists of chromium Cr3 plus, grossular consists of Al, aluminum, and andradite consists of ferric and titanium. So in eugrandite, the Y site has, the X site has calcium, while in pyral spite, the Y site has aluminum. So I hope you can remember this easily that the pyral spite, which consists of fixed trivalent ion in the Y site, while eugrandite consists of fixed divalent ion in the X site. So this is how these names are derived. The common forms in which the garnets occur, they are normally the rhombododecahedron. I'm sure you must have seen them in your practical classes in UG or maybe PG also, dodecahedrons. And these dodecahedron, they show 110, a Miller indices, and a very commonly occurring form is trapezohedron, which is 211. Now, based on the formula that we have seen, so the unit cell of garnet, it consists of X3, Y2, Z3, O12 formula units. Okay. Now, this formula unit, it consists of alternating, uh, ZO4 tetrahedra and YO6 octahedra. And once we look at the overall, you know, 3D network in which these octahedral and tetrahedral units, they share their corners to form this framework structure. So now this is what is the structure of garnet, and I'm sure by having the first look here you will be very much scared. What is this? So let me first explain this structure to you, and then I shall also tell you how to draw it easily. So as I have said here, that we get the alternating tetrahedra and octahedra. I'm sure you all are aware of what is a tetrahedra and what is an octahedra and what are the coordination numbers that go for it. Okay. So if you don't, just brush up on your knowledge about the classification of silicates and how the tetrahedra and octahedra, they are formed, and what is the coordination number. Remember that coordination number is always, it depends on the ratio of the cations to the ratio of anions. And those of you who are who need to brush up their concepts on the ionic radii should first of all go through the periodic table to understand how the ionic radius varies in a group and varies in a period. Okay. Now, so talking about the alternating tetrahedra and octahedral layers, as the name suggests, and these line diagrams over here, you can very easily understand this. So let us begin. So the first unit that you can see, it is a tetrahedra. All right. So this tetrahedra over here, it consists of, these four oxygens, and the black one over here, it is an it is the silicon. All right. Now this tetrahedra, this is another tetrahedra, the third tetrahedra. Okay. If you look at the between two tetrahedra, you get an octahedral layer. An octahedral layer is formed because here we are getting the coordination number of 6. So this is one octahedral layer and this is the second octahedral layer. All right. So we get the first top layer or first chain of alternating tetrahedra, octahedra layers. Okay. So these are the oxygens and this is silicon. All right. If you look carefully between the first layer. So let us name it as layer A. And now the same thing repeats in this layer B. So this is again a tetrahedra, octahedra, tetrahedra, octahedra. So once these two arrangements of alternating tetra and octahedral layers are formed, you can see in between these two layers of uh, TOT, you can find a distorted cube-like structure. This one, okay? Distorted cube-like structure. This one is a dodecahedron. Dodecahedron. So here you can see that this octahedron, you know, sorry, this octahedron, it coordinates with another tetrahedron to give a distorted cube-like structure, which is a dodecahedron. So you have one dodecahedron here. This is a tetrahedron. Then this one is again a dodecahedron, and this is a tetrahedron. This is how this entire arrangement keeps on sharing the corners to make a framework structure in 3D network. Now, if we look at this, uh, let me just draw for you. Okay, so here in this type of an octahedron, there resides the Y cations. So all these blue ones which you can see, this is the Y cation, and these yellow ones, they are the X cations. Now, why does this happen? Of course, a distorted tetrahedral is having, distorted cube is having a larger structure, and therefore it is equipped to accommodate the radii, the ionic radii, higher ionic radii. While the octahedron, which is relatively smaller, should accommodate an ion with lower ionic radii. Now, it is up to you to understand why these divalent cations, they are having larger ionic radius than those trivalent cations. So now it's easier said than done. Now let me explain how you can draw this structure. This is the whole idea behind this. Okay, so first of all, draw a tetrahedra. Not perfect, even a distorted one will do. Okay, a distorted tetrahedra. Now let me simply draw it this way. Then share its oxygen with the nearer tetrahedra again. So we have now this oxygen and this oxygen to form an octahedral layer. So let us first join it this way. So this is another oxygen. Then we have this one. Now in the next row, we again have a tetrahedra. So it is going this way, and then the one which is down. All right. Similarly, we have one more tetrahedra over here. Again, we will join its corners to make this octahedron, just like we did before. And then one over here, like this, here, here, and So I hope you understood now how these octahedrons are formed. Okay, and then remember, octahedron has a smaller space, interstitial space, than the dodecahedron. Therefore, it will be accommodating the smaller cations, which will be the Y cations. Okay, so this one and this one. All right. Now let us move to the next layer, which is the dodecahedron. So dodecahedron means we are going to have 12, centers over here, 12 points, and to make that we have this octahedron now combining with another tetrahedron sharing the corner. So it will be this way, like this, here, this way, and we have one here and here, like this. And of course, remember, we are making a cube which is distorted, so you don't need to make it a perfect cube. Over here, this way and this way. All right, now the lower one, that is I'm making with the broken lines. So I hope now you can visualize a cube over here. After this this dodecahedron phase, we have a tetrahedra, which is already existing over here, this way, this way, this way. Now this is a tetrahedron. Then again, with this tetrahedron combines the next octahedron, which will give us 8 plus 4, that is 12. So here, this one, this line like this, we are joining all these, and then the lower one. So we again got a distorted cube, and after that again we have a tetrahedron, this way. All right, now you have to remember, as I have previously mentioned, the more the space, it is going to accommodate the larger ions, that will be the X cation or X site. So the dodecahedrons, they have the X site or X cations, while the octahedrons, they will accommodate the Y cations, or it is the Y site. So it's easy. First of all, make a tetrahedra, then another tetrahedra, and join the corners to form an octahedron. And after that, in the next layer, join the corners of this octahedron to the corners of another tetrahedron to give a dodecahedron. That way, you will get the framework of alternate tetra and octahedral layer and eightfold triangular dodecahedron coordinating the X cation. So, if I simply remove the other things over here, sorry. So now I hope that you will be able to understand how this structure is formed. Just remember how the alternating tetra and octahedrons, they are placed. All right. Now, there are 6 commonly occurring species of garnets, as I have already told you, that eugrandite and pyrrolspite. But theoretically, it is possible to have 16 species. And each of divalent metals like calcium, magnesium, ferrous, and manganese, they combining with 4 trivalent metals of aluminum, ferric, manganese, and chromium. So we can have these 16 species, but of course, yes, naturally they don't occur like this. Either you have to, synthesize it under the conditions which are being given, or you need to have, you know, just theoretically possible. You have to understand it like that. Moving ahead. Now, the pyro garnets, you know, more than the formal 80% pyro is rare. Similarly, the pyrope garnets with Cr2O3 contents of 3 to 8%, they are common. Typical pyrope of metamorphic rocks contains about 40 to 70% of the pyrope molecule along with the almandine and grossular as other components. So you can understand this that no garnet will be occurring with 100% of its typical composition. Many such garnets, they are commonly associated with diamondiferous kimberlites. Almandine is the most commonly occurring species of garnets. Almandine. So these garnets generally contain, appreciable amount of both pyrope and spessartine molecules, and sometimes may also have grossular. Okay. Uh, you must have many times come across a word, garnet mica schist. So garnet mica schist, this rock at regional metamorphism, it may show a composition of almandine around 66%, grossular consisting of 25%, pyrope consisting of 5%, and spessartine consisting of 4%. So you can have a garnet like this as well, garnet composition. So that's what I was saying, that no garnet will be occurring with 100% of its composition. And a common alteration product of almandine is chlorite. You should know that. Okay. So as I've already mentioned, that garnets, they belong to cubic system occurring in rhombododecahedron and trapezohedrons as common forms. Sometimes also they may occur as distorted cubes. They occur in many colors. As we all know, color of a mineral is not the true property, but yes, garnet occurs in many colors, which include pale green, brown, black, you know, shiny brown, etc. Luster is vitreous, and fracture is concordal to uneven, having a hardness of 6.5 to 7.5. So once we talk about the paragenesis of garnets, so garnet is especially characteristic of metamorphic rocks, very commonly found in metamorphic rocks. Other than that, it is also found to occur in some granites, then pegmatites, uh, maybe volcanic rocks, and some kimberlites. Diamondiferous kimberlites, garnet is sometimes found to occur. And in sedimentary rock, it specifically occurs as detrital grains in sedimentary rocks. The commonest detrital varieties, they are almandine and pyro. So these are the most common varieties of garnets, almandine and pyro. Okay, all right. Pyrope, it occurs in ultra basic rocks such as mica peridotites or kimberlites, serpentinites. It may sometimes also be found in sands and gravel, which are derived from such ultra basic rocks. Then pyrope garnet, it also occurs as the gem variety in the debris of basaltic breccia derived from peridotites. And pyrope is one of the most diagnostic tracer mineral used in prospecting for kimberlites. So I give a multiple choice question to you, probably may be asked in GSI or other competitive exams, that pyrope garnet. So pyrope is a diagnostic mineral for kimberlites, and we all know why kimberlites are hunted. Okay. Garnets form essential component of eclogites. We all know that eclogites are ultra high pressure rocks, very heavy. So eclogites, garnets form an essential component in eclogites. All right. In the granite facies rocks, the garnets are typically almandine or rarely almandine pyrope. And almandine pyrope may also occur in blue schist facies rocks. Almandine garnets may also be commonly associated with igneous rocks, occurring in three different paragenesis. So in the igneous rocks also you may encounter garnets. Some less common garnet species like spessartine. Spessartine, it is commonly associated with skarn deposits. This is also another question for MCQs. If it is asked which of the following garnets is commonly occurs with skarn deposits, it's a spessartine. Maybe if I happen to make a lecture on ore geology, I will tell you about skarn deposits. Till then, please go and read about what are skarn deposits. Similarly, grossular, it is characteristic of both thermally and regionally metamorphosed impure calcareous rocks and also occurs in rocks which have undergone calcium metasomatism. Andradite occurs in contact or thermally metamorphosed impure calcareous rocks and particularly in metasomatic skarn deposits often associated with such metamorphism. And of all the six naturally occurring varieties, Uvaro white is the most rare. Okay, this was a rather short lecture about garnets, but the most important component of this lecture is this this structure. This structure is important, how you can make it, and once you learn making it properly, this will look like this diagram. Okay, so once you are asked about full question, maybe probably in the GSI exam about discuss in detail the classification and structure of garnet, this is how you have to go about it. Talk about the general formula of garnet, its basic properties, then the classification of garnet on the basis of six naturally occurring species, pyrrole, spite, and eugrandite. Then talk about the tetrahedral, octahedral alternating layers and how they combine together to form a dodecahedron layer. Make that diagram and then talk a little about the paragenesis, and it's my guarantee that you will be getting very good marks. I hope I'll be coming up with other mineral groups soon for your convenience. Till then, bear with me, read a lot. Good luck for your exams. Thank you so much. Take care.